Okay.
Okay, so yeah, my vague plan for today is not to really have a plan. It sort of reminds me of the way we used to have discussions. But I have to, oh well. I might talk about land bearings, and I'm going to start talking about children's drawings or dessins, whatever it's called. So one of the things I'd really like to do is, it's working? Yeah, okay. I'd like to straighten out how to take an arbitrary pair of permutations, I guess, jointly acting on the same finite set. So you can think of that as a what? That's like, it's an action of the free group on two generators. It's I don't know, a finite action of the free group on two generators. But we're going to take such a thing and we're going to turn it into a child's drawing. And in some sense that Grothendieck or somebody developed. I'm going to take a somewhat, as I often do, take a somewhat Coxeter diagram viewpoint here. Boy, I wish I understood this better. So there's this Coxeter diagram. I like using different colors to identify the different dots. And something very, not sure what the word is, something very unadorned about this Coxeter diagram, all those infinities. So there are no constraints there. These three generators that, well, three generators of order 2. So it's like free on the Coxeter group. Coxeter reflection group is free on 3 involutions, or whatever you call them, 3 elements of order 2. And the Coxeter rotation group turns out to be free on 2 generators. And I hope to see that. So what am I trying to draw here? This is the Coxeter tiling, hyperbolic Coxeter tiling on the Poincare disk, hyperbolic Poincare disk, whatever. Hyperbolic plane, Poincare disk. And it's kind of infinite on this hyperbolic plane, so you can't draw the whole thing, just start drawing little parts of it. And right, I guess one of the reasons I wanted to draw this is so that I could very explicitly figure out what my favorite generators are for the rotation group. So it looks like my favorite generators for the rotation group are, don't tell me, it looks like it's one of them is blue, red. That's also known as rotation around the green, I guess. I mean, if I'm starting with the element in the middle, think of that as like the identity element or something like that. Then, so yeah, so maybe I'll call this rotation around the green, but it's actually equal to change the blue, followed by change the red. Does that seem right? That will rotate us around the green cusp.
I think.
Okay. And rotation around the red cusp. That would be equal to, I mean, I could just look at the picture, but I seem to remember it's actually green, blue. Does that seem right, looking at the picture? Oh, did I say, maybe I should have said clockwise rotation. These are supposed to be clockwise rotations. I'm trying to, you know, use a fairly sane convention. Not sure that anybody else would use it, but so these are clockwise rotations. So that first one, blue followed by red, that was supposed to be clockwise rotation around the green cusp. And so this one I'm claiming is what? Green, blue? Did I say that right? Okay, so does that one work right? If you change the green, I'm not sure that's working at all.
Are you supposed to barycentrically subdivide these triangles?
I don't think so. I think that's, you know, probably associated with some different Coxeter diagram. Let me fumble my way through this because it really should work. So, okay, the first one I did what? So okay, I'm starting from the point of view, and then I flip the blue. So we're down to here. Oh, okay. I guess it does work. I guess I just have to remind myself that there are good and evil triangles here. And the rotation group preserves good. So, or I guess sometimes people also think of it that, you know, the reflection group has these triangular fundamental reasons, whereas the rotation group has what some people call a lozenge shaped fundamental region. So that would be the, you know, the maybe I can shade it in here. It's that whole lozenge there. So yeah, so did the blue-red, did that rotate to the next lozenge clockwise around the green?
Let's see, so if we change the blue and then we change the red.
So yeah, you know, there's a red right there. And yeah, and there's another little blue right there. So I'm trying to draw that whole second lozenge in there. And so one thing we should perhaps anticipate with the children's drawings is that it's the dividing line of the lozenge that becomes the line in the children's drawing. So you actually erase everything except for that little smile of the lozenge. I guess it's a little bit Cheshire-ish, I guess. And I don't think I noticed it first. That's a little bit, to me, that's a little bit perverse because you're erasing everything except for the dividing line. I don't know, maybe I guess there are, you know what I mean? I'd rather erase everything except for the boundary or something like that. But maybe people just use different conventions or something like that. Maybe I did just make unfortunate choice of convention. But anyway, I'm sort of stuck with this, that when we eventually, erase the scaffolding lines and be left with the child's drawing, it will just be those, what will be left to be those dividing lines, center dividing lines of the lozenges.
Am I supposed to understand that? Why? Or am I accepted for now?
It's just that that's the way the child's drawing game works. I mean, Grothendieck or whoever decided that, you could make the picture as unbusy as possible while still being able to completely reconstruct it from what you have left. And so all you need is if all you have is the edges, these edges that are connecting the greens to the reds, the green-red edges, that's enough combinatorial information to encode the whole Coxeter tiling.
Were those like edges from 0 to 1 or something like that in his?
Can I think? 0? I guess that's the way I'm thinking of it. I guess I'm thinking of those as 0 and 1, and the blue is infinity. That's you're probably not going to get yourself in too much trouble with that. No, I think that's right. Yeah, I think that's a good convention, because then people think of the edge as the unit interval, I think.
Uh-huh.
So yeah, I think it's going to be like that.
Can you?
Yeah.
Can you tell me what's red, green, and blue, or do you say green, blue, and red? And how they 0, 1, and infinity. So.
Oh, okay. Okay. Let's call them. Let's call them 0, 1. I mean, this is right. There's a lot of information packed in here that maybe is conflicting. So those things at the vertexes, those are just names, or these coordinates for the vertexes.
Yeah.
The black infinity signs, lemniscates or something like that. Those are just Coxeter edge information. Okay. Yeah. And so like I say, there are good and evil triangles. The good triangles are the ones that the clockwise, the colors, the vertex colors going clockwise are the way I prefer, which is green, blue, red. The evil ones have it, going counterclockwise. It's green, blue, red. Again, there's probably all sorts of conventions that work here, but yeah. So I mean, right? Somehow, right? I'm thinking of blue as being the third wheel here for some reason. I'm thinking of infinity as being the third wheel. It's like it's at infinity. It's very far away. 0 and 1 are much more at hand. So, right, somehow to get these things to work out clockwise, right, for some reason, I had to put the blue in front of the red to get clockwise rotation around the green. And for some reason, I had to put the blue after the green to get clockwise rotation about the red, if I did it correctly. Let me check that other one again, green, blue. So you've got there, you change the green, yeah, and then you change the blue, so you're ending up here. So yeah, that looks like you rotated the lozenge one lozenge clockwise around the red. Okay. So these are the two generators that the rotation group, the Coxeter rotation group, is free on. I mean, this is a good enough choice of convention of basis or whatever you call it for the Coxeter rotation group, those two generators. And so we can just, specify the, I don't know, maybe the generic fiber set or something like that. So let me give an example here. I'll call it we'll call it A, B, C, D. So we're going to be permuting these 4 elements. And so, you know, the rotating around the green, I'll put that in green color. So let's say that's going to be like, let's say, for example, this one. Oh, but maybe that means I should just have used, you know, cycle notation or something, right? Sometimes. But anyway, for the rotation around the red thing, which is green, blue, I'm going to have, I'm going to choose a permutation for that. And for this particular example, I want to make it abelian. So I'm going to pick something that commutes with that. And a possible choice is, you know, A and C are in a little cycle, and B and D are in a little cycle. So it'd be like, and those two commute with each other because I think this second one is actually the square of the first. So, you know, these two permutations commute with each other. I think your picture is not frozen, right? You're still here. You're just thinking. No, maybe your picture actually is frozen. You're very remarkably lifelike. All right. So I think I'm just supposed to wait here, I think. Hi.
I was gone for a while and back.
Yeah, I'm not quite sure how long you were gone because you looked very lifelike for some reason.
I was wrapped in thought. Yes.
Exactly. So,
well, like, no, I was gone for a while. So let's see. So you're drawing 2 permutations of a 4-element set here.
Yes.
And I see them. And one is.
And I drew them in 2 different styles. You know, I drew cycle notation in one case over on the right-hand side.
And so red is this rotation around red?
Red is the rotation around red, yes. Yeah. So I'll just call that. I don't know. Yeah, I'll call it rotation around red, and I'll call this one rotation around green. And one of the ways to think about what we're doing here is we're kind of taking an induced representation, an induced action. You know, we're kind of inducing from the rotation subgroup to the reflection group. And, you know, that's an index 2 subgroup. The rotations is index 2 in the reflections. So if you think about that, and if I didn't screw up too badly, then that means that, you know, you should think of the induced action as being on double the original 4 points. You should think of it as being, on double the original 4 points. So it should be on 8 points. And in fact, we could name those 8 points in terms of the sort of, you know, the lozenge thing. So again, blue gets you from one half of the lozenge to the other. Right. So each lozenge has 2 blue corners diagonally opposite to each other, but also 1 red and 1 green. That's what situation is with the lozenges. And so I could like, so yeah, we're going to kind of set it up like this. We're going to kind of set it up. What, you know, how is this reflection going to act? The green reflection. How is the blue reflection going to act? And how is the red reflection going to act? And because I'm using, you know, because of some convention I'm using that blue gets you between the two halves of the lozenge, it's just kind of, you know, automatic. I don't even have to look at the permutations to know how blue is going to act on the doubled set. It's just automatically going to be like this. It's going to be, you know, I'll call it the doppelganger, or whatever. I'll call it A bar. So we have that cycle, we have that cycle, and we have that cycle, and we have that cycle. Okay, so that's going to be the action. In a way, I'm just calculating the induced action here. So now, how is green going to act on this doubled set? So let's see. So green, okay, I got to check my conventions here. So the green, right, the green blue, that is the red rotation around the red. And I mean, it's just an automatic thing in the Coxeter group that green, blue, blue is the same as green, right? In any of these generating rotations, any of these generating reflections are reflections. They are involutions. They are ordered too. Mm-hmm. So you can just, you know, blue, blue is just another way of saying the identity. So, so to work out what green in isolation does, it's the same thing as working out what green blue does, followed by what blue does. And yeah, so again, let me try to help myself here. So this is green blue. And this one is blue red, if I'm managing to follow my own conventions here. So green in isolation should be ACBD, but then followed up with you know, putting the bars, putting the doppelgangers in, or something like that. So if I understand correctly, I think it's supposed to be this. I think it's supposed to be. It looks a lot like what green blue looked like, which was well, at least I think it's gonna be like. Let me get it. Let me try to get this here. Sorry. Okay. I think it's going to be, you know, A goes to C, except then C goes to C bar. And perhaps I should right away put in the other way around too, that C goes to A, but it's really A bar. And B goes to D bar, and D goes to B bar. So I hope those are the correct cycle notations for this induced action of the green reflection, the blue reflection, and then the red reflection should be pretty easy to figure out too. So should I go ahead and do it, or am I allowed to do it, or do you want to do it, or?
You're certainly allowed to do it, but maybe I should do it.
Okay, go ahead.
So
I'll try to think about it while you're doing it. Go ahead.
So we should have like a little duo of A, C bar, I think.
You're doing the red?
Wait. Why? Oh, what am I doing? Let's see.
Yeah, I have to think about this. Yeah. Yeah.
Why when you did why when you did the green one, did you use the pattern of root R?
And maybe I got it backwards. Let's see. Okay.
R
Well, it's because of these complementation games. It's because of these complementation games, I think. So, right. I mean, the rotation around a particular color is actually a composite of the complementary reflections. And then, right. You get clockwise or counterclockwise, depending on which way it goes. So I hope I got it right, that, rotation around the G, that's actually a composite of blue and red, right. Let's see. So you think, are you telling me I really got it backwards? Let's see.
No, probably not. But how did you figure out? Well, blue, okay. So blue, I see. Okay, sorry, I'm just slowly catching up. Okay, so blue, you just know because we know it. Okay, and so then.
In fact, I think secretly one way to think about it, it is an induced action, but it's an induced action involving a semi-direct product, right? There's actually, you just pick the blue reflection, right? So there's this, right? There's this homomorphism assigning to each triangle whether it's good or evil. And if you have a section of that homomorphism, you just need one evil one to give you a section of that. And so as soon as you have a section of a group homomorphism, you have a semi-direct product situation. So it is a induced action situation, but it's somehow easier than you might worry because, I mean, again, I'm being very sloppy here, but I think if you force me up against the wall, I think I can justify it. That.
Okay, let me try again. So
okay,
yeah,
go ahead.
Go ahead. So the idea is we know how acts. We're trying to figure out how red acts.
Yes.
And we know that blue followed by red cyclically permutes A, B, C, and D.
That's right.
So
that's right.
So like what should red do to A? So whatever it does to A, blue will have sent D to A, and then red will do something to A.
Say it again, blue will have sent D to A? I thought blue is the one that just formally puts a hat on things.
Sorry, I meant blue-red will send D to A.
Agreed.
Blue-red will send D to A. Well, maybe I don't care about that. Let's see. I want to know what happens to A. So blue will send it. Blue will send it to A bar. We want to know what blue-red does. No, we know what blue-red does. Namely that it sends A to B.
Right.
So therefore red has to send A bar to B. Right.
Can I give you my opinion on that?
Yeah.
That's what I got too. A bar goes to B. And I was just going to write.
Okay, so you can just write it down. Yeah, okay.
Okay, and then are you closed up with that cycle yet? Or?
I don't know. Let's see. It's an involution, right? So it has to end there.
I guess that's right. Right. So, by the way, as I was watching you, as I was torturing you, watching you do this. You started out asking what happens to A, and I was thinking to myself, he hasn't figured out yet that it's annoying figuring out what happens to A. It's much easier figuring out what happens to A bar, I think, or at least to me it is. And you ended up doing that. You said A bar goes to B.
Yeah, I'm still confused by, yeah, okay.
Sure,
because,
sure.
Okay, yeah, okay. So, right, okay, so that.
I've had a lot of practice, so I'm over a lot of my confusion, but go ahead, yeah?
Yeah. Yeah, so the idea is that like, we're first trying to figure out what red does. And what we know is that what blue followed by red does. And we also know that blue switches guys in their bars.
Yes.
So if you put in an unbarred guy and then hit it with blue, it'll turn into the corresponding barred guy. And so we're going to wind up finding out what barred guys what red does to barred guys.
I think that's right. Yes.
Yeah. So that's why it worked out that way. So, okay. Right. Somehow this is really tiring. Okay. So anyway, okay, I'll do it, but I should do another one. So,
okay, yeah.
So,
I mean, the tiring part is getting started when you're in the groove and doing the whole thing.
Right. Yeah, that's supposed to be how it works. Yeah, I'm not fully started yet. So it's still, okay. I know I'm at the stage where it's supposed to be not tiring anymore, but it still is for some reason. So, okay. So like, I want to know what happens to B, but I'm not going to find that out. I'm going to find out what happens to B bar, because B is going to go to B bar under blue, and then blue red is going to send it to C. So B bar is going to C. Okay, now I think it's finally gotten figured it out how it's going. So then C bar is going to D next.
Yes.
And then D bar is going to A. That's the pattern.
That's right. Yeah. So this is that. So now we have a very explicit action of the Coxeter rotation group. And to me, you know, I'm sort of trying to reduce this. Did I say it right? I meant to say the reflection group. Now we got the action of the reflection group. You know, the child's drawing game works with the rotations, the orientation preserving stuff, but the Coxeter thing works with the reflection. So we just had to adjust to, you know, right? I'm sort of assuming that I already know how to do the Coxeter case with all the reflections, the Coxeter reflection case. And I'm just trying to reduce the child's drawing game, which is all this stuff without the orientation reversing stuff. I'm just trying to reduce that to the case I'm already familiar with that includes the reflections. So, right, in other words, I already know how to work with the triangles. I'm just trying to exploit my knowledge of how to work with the triangles, how to glue the triangles together, to learn how to glue the lozenges together. And then, as an afterthought, it turns out you don't need the whole lozenge, you just need the little red-green edge in the middle. And from that's enough combinatorial information to reconstruct the whole children's drawing, to reconstruct the whole Coxeter tile. But this is a fairly good example to actually work out all the way. So let's keep going here. So what does that mean? Don't tell me. Let's see. Yeah. So what in the world am I claiming here? Don't give the answer away to me. What do I mean when I say that? Right. Again, I'm probably falling in the trap of being used to doing it now, and it's hard for me to explain it to other people because I'm so used to doing it. But let me try to figure out what I mean when I claim that this picture is almost manifestly giving us this Coxeter tiling. So don't tell me. Let me just think about it for a second. So let's see. Okay. So I guess right. So I guess the point is that there are these 8 little triangles. In fact, maybe I should draw them as, lozenge pairs. So what?
Yes.
So there's one like that. There's one like that. There's one like that. One like that. Why am I so bad at that? Damn. So these lozenges have 2 opposite blue corners. And I guess I'll put the good one at top. Sorry, that was supposed to be green. I somehow didn't click on it correctly. Green, okay. The greens I'm putting over on the left. So the good ones, the clockwise preferred ones are on top. The reds go over there. So what are we saying? I guess we're saying that this is like A and A bar. This is like B and B bar. C and C bar. I hope I didn't make any horrific parity error that's going to screw everything up. And we just have to kind of figure out how to glue these together. So what am I trying to say here?
So like flipping the green sends A to C bar. So should I take that good triangle called A and glue it to the bad triangle called C bar in such a way that the edge that they are glued along is the one that does not contain the green?
I think that's right. So yeah, something very much like that. Yeah, I was trying to listen carefully enough to be able to say whether it's correct. It sounded like it was correct.
Because you want to stick them together in such a way that when you flip the green, switch the green, you hop from the A triangle to
the
C bar triangle.
That's right. That's right. Because I'm looking at the green row there, and it says that A and C bar should get exchanged under green. But I'm just struggling to remember the last time I did this. I thought there was some slightly easy way to do this. Let me just think for a minute here. What am I trying to say? For some reason, I'm staring back at the rotation cycle things, like the rotation around the green. Oh, rotation around the green is all just one cycle. So I think I could sort of cheat and figure out from that means that there should really just be one central green in this final picture. Because as we rotate around the green, it's all going to give us one cycle.
And rotation will carry a lozenge. Now, what will it do? Rotation around a green will carry a lozenge to a lozenge.
Yes, it will. So, yes. So again, I'm kind of faking it here, but let me see if I can get something to work here. So I drew my central green there, and in some quadrant or other, I'll put something like this. Let's see, green, blue, red. Let's see. So let me think. Green, blue, red. Green, blue, red. Let's see. Green, All right. I'll try it this way. I mean, I think it's going to end up with, 4 of these lozenges rotating around the green. And opposite corner of each green is a red. So I think the reds are here. And yeah, and those are that, sorry, those are one color. These green red edges, those are the edges that are going to survive to the final child's drawing. And the blues, I guess, are like this. That didn't come out the right color. Blue. Okay. Well, let's try it. So let's see, green, blue, red.
At first, I was thinking that when you built this shape, it would have to be an octahedron, because I couldn't think of any other way to stick together 4 lozenges like that. But it looks like you're, well, am I mixed up? It looks like you're not getting it to be an octahedron. That is, you're drawing you're drawing 4 squares next to each other, which made me think, oh, good, it's working. But then you drew rays coming out from the middle instead of bisecting those squares in the way that we use to get a fold up octahedron.
Yeah.
Unless this is also an octahedron. No.
Well, again, I'm sort of trying to play fair, and I'm also trying to cheat at the same time. Again, because I've already done this example. Let's see. So clockwise, green, blue, red is supposed to be the convention. So I think that means I could take, since A is a good one, I could take. I think it might work if I take A there. And then what does that mean? That would mean that what? That where would A bar have to be? It would have to be over here. Is that right?
Yeah, that's the plan.
And this would be, okay, then what's opposite A bar? I think you told me it was, well, you might have told me what was opposite A. You may have said C bar. No, maybe that's not what you said. Okay. That doesn't look right, does it? So let's see, what are we doing? We're changing the red. Yeah, we're changing the red.
Yeah, if we change the red, then A is going to D bar, so.
Right, or maybe. I mean, we could even just think of in terms of the lozenge rotation thing or something here. But let me use the reflections. What are you saying?
Yeah, don't get too fancy. So I mean,
okay.
Actually, I mean, what we're doing is as we keep, like if we change the red,
yeah.
Let's say that A bar goes to B. Let's keep the pattern that it's easy
right there.
Yeah, I mean, it's easy to see it's written in such a way that you see where the barred guys go. Well,
okay. So B bar is right next to the B.
Yeah,
that's what you said.
Yeah.
Okay, and then where does
goes to C?
Yeah.
Then we get a C bar next to it.
Okay.
And C bar goes to D.
Okay.
I've got a D bar next to it. I think that's what.
Okay.
I think that's what I'm saying.
And then, then I guess, if I remember correctly, it seems like really looking at the green changing thing is really going to tell us how to glue the boundary edges together. So let's see.
So when you change the green, you still get to the same green because there's only one green.
I think that's right. I think that's right.
But But you still change, yeah. Uh-huh.
I think that's right. I think that's right. So I'll just, you know, I only used up the first 4 letters of the alphabet, so I can go on for further letters of the alphabet to give the names of these, you know, common edges. So I can call this common edge E. And what is it common with? It's green applied to, you know, when you flip the green on the B bar, you get D. So this should be an E over here. Boy, I'm not sure I like that. Is that really the way it's going to be? I guess it is.
B bar goes to D, yeah.
And when you flip the what? When you flip the
I can do these. I can so
faster than me, probably. Yes. So what are they?
So like C.
We're going to call that F. I can christen that F.
Okay. Sorry. So
Okay.
that one goes to the one next to A bar. So the other F is near A bar. So that's like, that's really weird. Yeah.
Okay.
And then C bar.
I'm going to christen that G.
G. And then C bar is getting sent over to A. So you want to stick your G next to your G, other G edge next to your A. And then you get a.
Is that really true?
It looks crazy because they're like all over the place. I was hoping that they'd be sort of like in some cyclical thing or something, but I don't know why I was hoping that. I mean, I'm following a rule, and you seem to be verifying that it's probably maybe like.
Yeah, but I'm really a little bit
like
spooked here. Is this really even consistent? Let's see. F G. Oh, maybe it works. Maybe it's consistent.
Okay, well, let's move on to the final edge H, which is there's only one thing it could, only 2 things it could be.
So you're gonna have it put it over here?
Yeah, and it's.
Oh, you're just saying put it on whatever.
Yeah, there's no more room for anything.
Okay, okay. And now I'm hoping that this actually does make sense. But in particular, I think it shows that I sort of picked a stupid or unlucky convention or something like that, right? Maybe if I had drawn it like somehow if I had drawn what's going on here? Why am I screwing up here? If I'd drawn it like this instead, maybe, or I don't know what I did wrong, but I must have committed some horrible sin because it sort of came out unlucky, I think. What if we have it be like this? So it's still blue at east and blue at the cardinal directions.
So is this supposed to be just another way of drawing the same thing? Or is this a different?
This is, yeah, no, this is the same thing. I'm just, you know, well, let me put in the labeling and you'll see that this is just a better way of doing the same thing.
Okay, yeah, I see. You just stretched.
Yeah, so
stretched it out in a certain sense.
B bar, C bar, D bar. You know, I think it's combinatorial. It's just the same as the previous one.
Okay, good.
But I think it just works out a little bit better. So what do we got? We got like this is like FG. This is FG. This is HE. And this is HE. Yeah, I think this is now working out correctly.
Why is it working out better? I haven't figured that part out yet.
Well, because when you look at the boundary identifications, it's just classic torus.
Oh, okay, good.
And it seems to me this must be the Gaussian elliptic curve. Because I mean, it's just right. It just seems like combinatorially it had this square symmetry. So, you know, the geometric realization of a child's drawing as a Riemann surface, that's got to be functorial enough that can preserve that square symmetry. And so the only thing I could possibly think of, if I'm not screwing up, is that this must be the Gaussian elliptic curve that has that kind of square symmetry.
I'll buy it.
So I mean, you know, I just really have to practice this this procedure, and you know, it's kind of, I mean, this is, in a way, this is completely basic and obvious, but I really had to practice it a bit. I mean, it's just to sort of learn how to remind myself how to connect up the Coxeter combinatorics with the children's drawing combinatorics. And, you know, it really helped to remind myself about that this is kind of an induced action, inducing the action from the rotation group to the reflection group. Just helped me understand what's going on. And yeah, so again, I mean, I just liked, I had some reasons, I still have some reasons for studying the abelian case. So we picked an abelian example here. And I don't know, it's interesting that it turned out to be such a simple example. It's interesting it turned out to be the Gaussian elliptic curve. But we, you know, we shouldn't be stuck with the abelianness. I mean, everything we did here should have pretty much worked the same way, even if we were doing a non-abelian example. Maybe we should just kind of do a non-abelian example, okay? So, I mean, right, I can always use more practice. You probably use a little bit more practice too. So let's just try to do another example here. So what would be another interesting example here of a group that's generated by two elements, a finite group that's generated by two elements? So it seems to me like there are some obvious, interesting examples. You could have, you know, any n bang. Is that right?
That'd be, I was
Say it again?
I was thinking of 3 bang just to keep it small. I think you could do that, right? So I don't know. Yeah,
yes, you could do it 3 bang. You could do 3 bang.
Were you wanting to do 4 bang just to make it more like the last one or something?
I was thinking that if we did 5 bang, it wouldn't be that bad. Oh, maybe you think it would be that bad. Let's do 3 bang. Okay, let's do 3 bang. Well, and so is that non-abelian? I guess you're telling me that that is non-abelian.
Yeah, I was trying to do as little work as possible.
Okay, fair enough. Fair enough. I mean, when I started thinking about these, I was a little bit shocked at first that these exist. Because it's sort of obvious. It's sort of obvious. What?
Did what exist?
That this child's drawing exists. Because I mean, I think, if I'm not screwing up, it's sort of obvious that when we work this out, that this is going to be, or at least if we do it in a certain way, that it's going to live, you know, that the Riemann surface is still going to be the Riemann sphere. So it's going to be a sphere. So we're saying that.
Sorry, for 3 bang, you mean? Or?
For 3 bang, yes. But what if it were arbitrary? What if it were n bang? What if it were, you know, 23 bang? I was a little bit shocked by the idea that 23 bang, maybe I shouldn't have been shocked, but I was a little bit shocked by the idea that 23 bang acts on the sphere. You know, I'm not used to seeing a sphere that's decorated in some way that it has 23 bang symmetry.
I don't know why you're getting the sphere from these examples that we haven't done yet.
Okay, let me try to convince us that we're going to get this here. So,
by the way, I don't think we've squeezed all the juice out of the Gaussian one. In one,
I agree.
Way. We didn't even draw the child's drawing in some kind of
let's go back and do that.
Traditional style of child's drawings.
Let's go back and do that. Well, so in some sense we're supposed to draw it on the torus, but let's see. So we're supposed to only include the red-green edges.
So we can just take that diamond you drew.
Yes.
And think of that as the torus. And then I guess you're saying we only draw the red-green edges.
Yes.
So
it looks like it's really just got 2 reds and 1 green. Is that right?
Yep.
So maybe I could draw them. What am I trying to say?
Red is 1.
I mean, right, I've seen, as I've been browsing, reading articles and books and stuff, I've seen people who are competent enough to, draw a picture of a torus in the traditional caustic way or something. Sorry, what's going on here? How do I undo this? Okay. Right, I mean, I've seen people draw this picture and then draw a child's drawing on. Is there some way we could transfer this picture that you just mentioned? So let's see. So you're saying...
Yeah, you just need to sort of draw the longitude and the meridian of this torus. And
okay, so you're saying just put a green in our favorite place, and then put one red half the longitudinally opposite, and then the other one meridianally opposite, or something like that. Is that what you're saying?
Yep, I guess so.
It could even be that I've seen this one drawn on some book cover or something like that. So how does that actually work? It's like, is there like a red over there, and there's a red maybe on the inside or something like that? Maybe it's one like that. And
then you just draw, along,
something like that, and something like this is a very bad picture, but so are you telling me?
Yep. Yep.
Sorry, screwing up here. Red. So it's like a red and red and something like that. Okay. So yeah, I mean, it's fun that this is genus 1. It's fun that it's the very classical, seems to do this very classical Gaussian thing. It's fun that it's abelian. It's fun that having non-trivial genus, you think about it's Jacobian. Of course, Jacobian is just itself, since it's only genus 1. But if we got to higher genus, then we could start thinking about the Jacobians of those higher genus things. And I'm very interested in learning about Abelian variety. So that's just another potential learning opportunity here, to learn about the Jacobians of children's drawings, of higher genus children's drawings. But on the other hand, right, it's also supposed to be interesting to just look at children's drawings that it's supposed to be interesting enough already to just look at the child's drawings that live on the sphere. And I think we're going to get some examples of those. So let me give you, what? Were you saying something?
Okay. Yep. So let's go. Yeah, let's do S3.
Okay.
Yes.
Okay, so maybe I can start the alphabet, beginning alphabet again.
Sounds good.
So one of them is like that, and the other one's like that. And remember my conventions here. It's blue, red was the, yeah, blue, red was the green, rotation around the green. So this is blue, red. And this next one is green, blue. Right, I mean, right when, presumably, there's probably people who just like, maybe either they just had more practice or else it's just obvious to them that you don't even have to think in terms of these, maybe, right? Some people just directly draw the children's drawing without even thinking about the triangulation. They just directly draw the lozenges or just the smile part of the lozenge without even thinking about these two. But I think, right, even some of the standard textbooks on this stuff, they talk about the canonical triangulation of the children's drawing or something, which you add in these extra scaffolding lines, these extra auxiliary lines, which make it into a triangulation. And it's like combinatorially unique, but I think you actually have to sort of pick some random places to draw the extra dots or something like that. But it's combinatorially functorial or whatever. But I'm just imagining that some people might just, they might know how to immediately directly draw the children's drawing without thinking in terms of the triangulation. But okay, so what have we got here? I guess I'm not one of those people, so I'll go ahead and I'll draw separately the green reflection, the blue reflection, and the red reflection, and the blue reflection always just in cycle notation, always just kind of A and A bar, B and B bar, C and C bar. And so, right, so green alone is the same as green, blue, blue. So that should be the same as A goes to B bar and B goes to A bar and C goes to C bar, I think. If you can try and catch me in any mistakes or something like that. So the red is the same as red, blue, blue. No, same as blue, blue, red. So it's like I take the A, B, C, that length 3 cycle, but I just put the bars in front. So it's like A bar goes to B, and how does this work? A bar, right? A bar goes to B, and B bar goes to C, and C bar goes to A. Yeah. So those are those 3 reflection permutations of this 6-element doubled set of the 3-element set ABC. So okay. Now it looks like the rotation around the green, once again, is going to only have one single I think I think this is another good one where we could put the green in the middle. The green does not seem right. And it's going to be something like, I don't know. And blues and reds kind of alternating or something like that. And sorry, wrong quote. Why did it come up such a screw? Okay. And so where is like A, or where can we put A? A is a good triangle. So I guess I you know, maybe it'll work out nicer if I make a different choice, but I can put the A right there, right? Can't I? And that would mean A bar would be there.
Yep.
Seems right?
Yep.
Okay, and then what? The red changer changes A bar to B.
Yep.
And then it must be C and C bar. But let's see, is it obvious? So the good one is green, but yeah, this should be C and this should be the evil one, C bar. Okay, and then we got some edge identifications. So I'll start using D, E, and F. So let's call this one D here. And it's the green one, takes A to B bar. So this is D over here. What does that mean? Not sure what I was expecting here. Let's say E over there, maybe. A bar. That's going to go to B.
E, yep.
So it's right there. And that makes it seem like this is going to be F and F.
Yep.
So you have a clear picture in your mind of how this.
Yeah, I guess it is nice. It's just sort of like folding a disc over, forming a sphere out of it.
Can you draw it for me or something like that? Oh, yeah. Well, I mean, you have your drawing thing. What are you saying this Riemann sphere looks like? You're saying there's a green. Or yeah, okay.
I would like draw the prime meridian as this line subdivided into 3 parts called F, D, and E. Well, I don't know why I'm doing it that way. Yeah. If like the North Pole is red and the South Pole is blue.
North Pole is red. South Pole is blue. Can I just stare at it for a moment? I'm just not oriented to the picture yet. Let me just stare at it for a moment, see if I understand what's going on.
I mean, to me, the big surprise and clue is that you've got like FDE on the outside.
Yes. Okay. I see what you're saying. FDE. Okay. So you got like FDE. So it's going. Don't tell me. Red, blue. Sorry, why did I draw green down there?
Yeah, red, blue, red, blue.
On the prime meridian. Why is that? Why not? I was trying to draw a blue. Blue. Okay, and also down there. And on the international date line, we have just a green or something, is that right?
Yep, equator, opposite this.
Equator? Let's see. I mean, maybe, let's see. Maybe, yeah, I don't know really good choices to make here, but maybe I could, you know, have the view the prime meridian sort of edge on, if that makes sense. Red,
yep.
Blue, blue, red. And then you're telling me there's a green over here?
Yep.
And
so those other, let's see, all the reds and the blues have a unique edge going to that green. So you've drawn two edges going to the green so far, but there are edges from the other red and blue to that green also. It's weird.
Sorry.
Yeah. Well, except for the color. Yeah.
Right.
Line.
Is that what you're saying?
That's what I'm saying. Is this right? It looks like somehow we drew the picture so like everything interesting is happening on the front of the globe. The part we can see.
Yeah. Okay. Yeah, and the whole edge counts as the whole silhouette or whatever counts as. But let's see. So, I mean, okay. So this actually lives on the Riemann sphere, but I can use stereographic projection. So I can just draw it on the plane. And I could just draw.
Was red supposed to be 0 or 1, by the way? Right now we're drawing.
Do we have to decide?
What? We had decided once. We had decided that red was 1. Okay, that's sort of too bad. Our picture looks like red and blue are opposite. Well, one of the reds. Nah, never mind.
You know what? I think I might have the picture wrong. Let me try to use the stereographic projection, okay? To tell you what I think it looks like. And maybe this is what you already, maybe I drew it wrong, or maybe I misheard what you said, or I don't know. But if I use the stereographic projection, I think it's going to have the one green, and it's going to have the 2 reds, and it's going to have this green-red edge, and it's also going to have, am I right, these 2 green-red edges?
Oh, so then not everything okay. So I had said that like the weird thing about the other picture was that like all the edges were in the visible front of the picture, but we didn't draw 2 edges between a red and a green. So but you're right that there should be there. So there's like a secret extra edge from a red to a green behind our first picture. But anyway, in this style, it's all laid out.
Maybe it's, yeah. Maybe you're telling me it was like there or something?
Yeah,
Oh,
yeah, that's what I was imagining. It's like a secret back edge there, yeah. It sort of had to be because otherwise we weren't dividing everything up into triangles. Yeah.
So now I'm really trying to remember, is this the way it came out the last time I drew this example? Did I actually do this example?
Yeah, I think there are also like two edges from that blue to the green. Because notice there's one blue, one edge to a green, and one blue that has two edges to a green.
Say that again. I missed what you said. Can you say it again?
Yeah, in our hexagon there, you see there's like one blue that has one edge to the green, and there's another blue that looks like two blues, but it's one other blue that has two edges to the green.
So, so I should have drawn that out. Also.
Yeah, I think there's also like another back. Yeah, that's what I'm gonna do. Yeah, do it. Yeah, you're doing what I would do is draw another secret. Yeah. Now the whole thing is triangulated. Before it hadn't been really triangulated. The sphere hadn't been triangulated. But anyway, maybe it's all going to be clear in your new style of drawing it on the complex plane.
Right. Well, I mean, again, if you just draw the child's drawing, then you're supposed to be able to functorially reconstruct the triangulation from it. And so, what do? You put where do you put the blue dots? Again, you don't know exactly where to put them, but combinatorially where to put them. But anyway, it sounds like you're telling me when I drew that sort of bad globe picture, it finally ended up being a triangulation. It looks like it's got 3 triangles on the front and 3 triangles on the back or something like that.
Huh.
So yeah, but just for a moment, let's imagine that instead of doing 3, that we had done 23. Okay?
Okay.
So let's just see if we can like combinatorially count the Euler characteristic in that, like let's do it in this 3 case, but let's also do it in the 23 case. So what am I trying to say? That we've got so I guess we're doing this example of n bang generated by what is it called? A cycle and a transposition. That's kind of the example that I want to do. And this is an example of that with n equals 3. But now we're doing with arbitrary n. So the Euler characteristic should be, negative n. Is that right?
What are you using to guess the Euler characteristic?
This is kind of that Riemann-Hurwitz formula that you looked up for us somewhere. I mean, some version of the Riemann-Hurwitz formula. You said it was slightly different, but I'm trying to. N is the total number of sheets on this branch cover or something like that. And for some sensible reason, that counts as negative in the Euler characteristic calculation. And then you have plus let's see. So one of them is just a cycle. One of them is a transposition. So the cycle just has 1 orbit. The transposition has 2 orbits. Why isn't this coming out anywhere near what I thought it would be? What am I trying to say? Did I do the calculation wrong this time? I thought I was going to end up with some sort of I thought I was going to get the Euler characteristic of the sphere for this arbitrary and bang thing.
I don't get how you're calculating this Euler characteristic. So for all I know, you're doing it wrong. But...
all right. Let me just struggle with it privately for about 10 seconds or 30 seconds here before I give up and ask you to explain it to me. So let me just stare. Why is this totally not coming out the way I thought it's going to be? I mean, there's something to do with the idea that you've got, well, so I'm trying to look at rotation around the 3 branch points. So, one of them is, okay. No, it is working out right. Yeah, we're trying to figure out the number of orbits of rotation around each of the 3 branch points. So this version of the Riemann-Hurwitz formula says something like that you take, the total number of points being acted on, and you count that as negative. And then you look at the orbits around each of the 3 branch points, and each of those numbers of orbits counts positive. And I mean, this is just, the Shanuel-Euler characteristic. You're just, but it's a lot like the original Euler characteristic. It's just, vertexes count as 1, edges count as -1, and cells count as +1. Yeah. Somehow it's going to work out. I mean, so. Right. I mean, right. So, I mean, the Euler characteristic of a 2-hole annulus, or also known as a pair of pants or something like that, that is -1. So that's the generic fiber. That's the total number of points. That's why we're counting it as negative.
Okay.
Yeah.
Okay. Now it's finally starting to make sense. Okay. Yeah.
Okay. And then you count the special fibers, and the special fibers are just the orbits of each of the special rotation permutations. So yeah. So we're generating by a permutation. So we're generating by a cycle and a transposition. The cycle has very few orbits. The transposition has lots of orbits. Right, the cycle is just 1 orbit. So yeah, so it's okay. So it's -1, -n, I think, -n, plus the orbits of the cycle, plus the orbits of the transposition, which would be n-1. Is that right? The orbits of the cycles of the transposition permutation there's n-1 of those cycles. And then you have to take, the composite thing. And I think that's got 2 cycles, right? Is that right? I think I'm getting like this for my Euler characteristic. So first of all, you can see that it's independent of n. The n's cancel out.
Yeah.
So yeah. So if the first one came out to be a sphere, they must all be spheres because it's independent of n.
Yeah, I'm still confused about how you're counting this Euler characteristic, but
I'm doing it in a very sloppy way. But it's like what you said. I mean, so we're looking at the bulk and we're looking at the special fibers over the 3 points. And for the bulk, that's like an open annulus or something like that. no, an open two-hole annulus. So that counts as Euler characteristic -1 times the number of elements being acted on. So that is, that counts as -n.
Okay.
And then for each of the 3 branch points, for one of them, I'm getting 1. That's the branch point that's acting as a cycle, which in this case is, that looks like rotation around the green. I have it set up here so that rotation around the green is giving us the cycle. So it's just got 1 orbit. That fiber is just 1 point.
Okay.
And the transposition, that has n-1 cycles. So n-1 points in that fiber.
And then the other is the composite of those 2.
Yeah, or perhaps it's the inverse of the composite of those 2. But either way, it's got the same number of cycles. The inverse has the same number of cycles as the original permutation. So, yes.
And that other element, it's, what's that other element like? The cycle composed of the transposition?
Yeah, it's, rotation around infinity, rotation around the blue. So one way it would be green, red, the other way it would be red, green. I forget which is which, but green, blue, blue, red. Yeah, it'd be red, green would be the clockwise around infinity. And yeah, so if you compose a cycle with a transposition, it just kind of breaks up the cycle into 2 pieces.
That's what I wanted to know.
If I remember correctly. You know what I mean? It breaks it up into 2 pieces right at the 2 pieces that are, it's like you're cutting it right at those 2 points that are being transposed.
Yeah, okay. So I'm having trouble thinking about that for some stupid reason, but that sounds
sure.
familiar. So
again, I'm trying to play fair and cheat at the same time, so it's like
that's like double cheating, right?
Exactly. So let's see. It looks like the 1s and -1 cancel out.
Yeah. So you're getting
just left with a 2,
which is what you.
So you're getting a Riemann's here.
Okay.
So you're getting a Riemann's here. So that means, if I understand correctly, that's saying that n bang acts as symmetries of the sphere. So is there something like, I looked this up, there's somebody like Smith or somebody, is that their name, who investigated group actions on spheres or something like that. Finite group actions on spheres or something like that. But I don't think I ever appreciated just how many groups act on the 2 sphere. I mean, because again, I was thinking, you can make a 2 sphere look like a dodecahedron or something, and then you have that 60 element group acting or something like that, or 120 or something like that. But I think I can get any n bang to act on the sphere, but it must be that it's not acting metrically, something like that, right?
Yeah, no, it can't, because there's the only rigid actions on the sphere, the sort of famous ones. That's the sort of
but apparently there's all these non-rigid actions that I never noticed or never appreciated or something.
Yeah, those are interesting and weird. Yeah.
You've run into those before?
No. I'm just saying that they're interesting and weird. Yeah.
Sure.
It reminds me of how n bang shows up so much in Galois theory, sort of like a generic option for a Galois group of a polynomial with n roots. We're sort of having this, we keep bumping into this thing where you're like, well, like before you were talking about like finite Galois groups, abelian finite Galois groups, and also abelian Childs drawings. And I was saying, like, can you like relate them? So I'm going to say the same thing again now. Like, can you relate these covers of the sphere that you're just discovered to some number fields that have Sn as their Galois group?
Yeah, okay, that's a good question. Those are good questions. You're sort of hinting at a whole bunch of questions here. I don't have a really good answer for that yet, but yeah, those are good questions to think about.
Yeah.
Right, I just thought it was interesting. You know, if you're trying to learn about college drawings, it just seems like there are these examples lying around that seem kind of interesting. That, you know, and bang, it's obviously generated by two elements, so you're getting something there.
Do you know how to? Yeah, it is interesting. Do you know how to draw the child's drawings for any of these ones beyond the one we just did?
I did practice it like a week ago. I think I've already forgotten what they look like. They're very simple. I'm trying to remember. Let's see.
Some simple generalization of what you just did.
It's pretty simple, but I actually forget.
So I believe we had like one green.
If I try to draw it, I'll probably draw it wrong. But go ahead. Yeah.
We just
it looks like a little cross or something.
Oh, okay.
What am I trying to say?
I was just trying to think of some generalization of the picture we did. The picture we did had one green and two reds. And the two reds was the n-1 in your formula?
The two reds.
I think. Or, well, not necessarily. Maybe it was the two.
Yeah, how does this work? Let's see. By the way, I have the feeling that if you draw this right, maybe you have to like permute the colors or something, but you can get this to be one of those tree things or something like that. Right? We read something about some children's drawings are just trees or something like that.
Oh.
I have a feeling that that's showing up here somewhere, but I can't quite remember what's going on. I'm struggling to remember what I thought I calculated. I thought it was something like, I thought I got something that looked something like Sorry. I'm really having trouble remembering how this went. Like you say, right? There should be. Oh, I think I permuted the colors. Right. I think I had it set up that you only. Right. Let me think for a moment. Right. I mean, you're just supposed to draw the unit interval, but maybe I was pretending that instead of having blue be the infinity, maybe I was having green or red be the infinity or something like that. Because I think I wanted to not draw the one that just has the one. Right. I think I want to have like just draw the blues and the reds or something like that. So so what would it be like? Let's see, the blues and the reds. Blues. There's something that has like two of one color, and then it has another color. Maybe it's like, I'm really having trouble remembering how it went. Let's just leave that as a homework exercise for now, okay? It's a perfectly pleasant picture.
Uh-huh.
because I want to, you know, instead of stumbling through doing that, I want to stumble through trying to do some other stuff before we quit.
Okay.
So, but yeah, right. It's good to really draw that. And then, right, what are some other good examples? So some other good examples are the ones that are these very classical ones that are like, you know, actually end up being modular curves and famous modular curves like PS, the ones that are related to P, you know, PSL 2 comma Z mod P or something like that. And you can find pictures of those around the internet and stuff like that. Those, in fact, I remember back when I didn't really understand a lot of this stuff, but I understood some other stuff. I remember drawing pictures of those modular curve examples of children's drawings, which are related to P, you know, PSL 2 comma Z mod P as a group that can be generated by two. Right. So it has, right. What am I trying to say? I mean, I think we decided that PSL 2 comma Z is maybe the free product of Z mod 2 and Z mod 3 or something like that.
Yep.
And then there's some non-free coarsenings of that. But it's still generated by an element of order 2 and an element of order 3. Anyway, that's another good example to work out, is those modular curve flavored examples. And those, in a way, those seem very different from these n-bang examples. Is that right? They really do seem different from these n-bang examples, right? Because those modular curve examples, they have to be just generated by, you know, one permutation of order 2 and one permutation of order 3. Whereas these n-bang things, that yes, they're generated by one element of order 2, but the other thing is not of order 3. It's of order n. It's like a cycle or something like that. So not sure what to make of that. But you know, there's all sorts of things that I want to look at here, and all sorts of things that I won't get to today. So, for example, we want to, as an example of one of the things we won't get to today, is we really want to understand how some group that maybe is some group or groups, maybe it's called the Grothendieck-Teichmüller group, or maybe that's the same thing as, or almost the same thing as the, is the group called the Grothendieck-Teichmüller group? Maybe it is, but
there is such a thing, yeah.
But it may also be very closely related to, or might even be conjecturally the same as, I don't know, this absolute Galois group of the field of rational numbers, which I guess is the absolute Galois group in a way. And that, I mean, this is kind of getting into your remark about, you know, trying to get multi-level games where different Galois groups interacting here. But perhaps this is interacting in a different way, a different, not so much an analogy, but one acting on the other. I don't know, but there's all sorts of possibilities here. But yeah, there are all sorts of things that we'd like to learn about that, perhaps that absolute Galois group of the rationals that acting on these child's drawings, turning one child's drawing into another, if I understand correctly. And I guess you've explained to me a little bit about how that works, but I really want to think about it some more and perhaps not talk about it today, perhaps mostly because we don't have time to talk about it today, but also because I don't think I have much intelligence to say about it yet. But before we quit, I do want to talk about something else. I just want to keep on exploring. So I'm interested in these abelian child's drawings. And by the way, if we do think about how the Grothendieck-Teichmüller group or the absolute Galois group of the rationals, if we think about how that acts on these abelian child's drawings, I have a feeling it might end up being a completely trivial action. It might be that the abelian drawings are actually fixed under this Galois action. I don't know if that's true yet. I didn't check things carefully, but I mean, even regardless of whether it's true, I'd like to know. So one thing that'd be interesting to know is, are there a bunch of children's drawings that are fixed under this absolute Galois group or this Grothendieck Teichmüller group? So I'm right. People play games, or at least I have these old books. Maybe by now people have resolved a lot of these questions, but I have these old books that say things like, you know, it's interesting to try to characterize the orbits of this Grothendieck Teichmüller action on the child's drawings. It's interesting to try to
hold on just a second.
Go ahead.
Lisa? Oh, never mind. I think it's working.
Okay. So it's interesting to try to give as best as you can, as close as you can, try to give like graph theoretic characterizations of the orbits of this Grothendieck Teichmüller action or something like that. And so one of the things I thought about is try to give a sort of graph theoretic characterization as best as you can of the singleton orbits, of the things that are actually fixed, because I think there are. I think. Right. I mean, doesn't it seem like? I mean, you know, I think we've already convinced ourselves at on different days that the Gaussian elliptic curve and the Eisenstein elliptic curve, that they both show up as abelian child's drawings. And I think they both show up in such a way that, you know, you said like, you just look at how the equations you get. And, you know, they're supposed to be defined over this Q bar thing. But if they're defined over 2, then they're fixed under the action, under the Grothendieck Teichmüller action. And so,
okay, I get it now.
The Eisenstein and Gaussian ones are certainly fixed. I think it might end up being true that all of the abelian ones are fixed under this action. So I don't know. But I want to explore a little bit more concretely what these abelian ones look like. I mean, it could be that, you know, it could be, I mean, I have good reasons for being interested in it. I think I have good reasons for being interested in these abelian ones. And again, it has partially to do with, as you were indicating before, these attempted analogies between the number theory and the children's drawings, the number theory and the geometric Galois theory, the arithmetic Galois theory and the geometric Galois theory. So I have reasons for being interested in that. Some people might consider these abelian child's drawings to be too boring or something like that, but they're not too boring for me. You know, they're already exciting enough for me. So I want to think about these. I want to think about the general abelian child's drawings now before we quit. So let's think about this. So if I understand correctly, that should mean that we should, I mean, I think we can sort of think of it from the point of view of the universal abelian child's drawing. So, I mean, right, you can go back to this picture, where was it? Up here? Sorry. This picture here that we didn't draw very much of. This is kind of the universal child's drawing, or particularly if you just, you know, if you're only drawing the red-green edges of this picture up here, this Escher Poincaré disk, Escher tessellation thing. But if you just only draw the red-green center edges of the lozenges, then that's sort of the universal child's drawing.
Yep.
But if I understand correctly, we could instead try to draw the universal abelian child's drawing. So that would involve, you know, instead of taking this free group on 2 generators, we want to coarsen it to the free abelian group on 2 generators and see what that looks like. And this won't be a Coxeter group, right? Because I don't see any evident way in which it will be a Coxeter group. I mean, right, we're not imposing Coxeter flavor relations now. We're saying that these rotations all commute with each other. Right? The Coxeter flavor of relations are where you assign orders to the rotations, to the basic rotations. But here we just want to say that the rotations commute with each other. So I'm sort of expecting that this is going to be, you know, we can sort of draw this as a Coxeter tiling, but it won't come from a Coxeter group. It will be this funny coarsened version of a Coxeter group. I'm expecting it to have some sort of funny genus or something like that. That's going to be, I don't know, we'll see how it goes. So another way to think of it is, you know, we said that we can take any pair of permutations and we can get the child's drawing from that. Well, we could do that to, am I saying this right? What do I want to say? I want to say something that we want to do that to the sort of universal abelian pair of child's drawing. Universal abelian, sorry, it's like the universal commuting pair of permutations or something. What do I mean by that?
Well, it's like the action of Z2 on itself, Z squared on itself.
I guess that's right. Yeah, I guess that's right. I guess that's right. Yeah. That's right.
We were drawing those n by m rectangles the other day.
Right, but now this is, that's right. But now this is a limiting case of that where it's infinite rectangles or something like that. So yes, we were definitely on the right track when we were doing that, when we were drawing those rectangles. But now,
probably should be, I don't know. You're making me think of like using this profinite completion of the integers in both directions. Because the way that those n by m rectangles are related to each other, I think is if n divides n prime and m divides n prime, I think.
That sounds pretty much on the right track. I mean, all these infinite groups here that we're talking about, you should probably profinitely complete them, perhaps in some very functorial way or something like that. So like the free group on two generators, I'm sort of expecting that what we're really dealing with here is like the profinite completion of that free group on two generators. I didn't really check up on whether people think of it that way. But probably that's the way they think of it. And, you know, so the continuous actions of that profinite completion, universal profinite completion of free group on two generators, the continuous actions of that should just be, if I understand correctly, if I'm not making some stupid mistake, that should just be the finite actions of the free group on two generators. And you're suggesting something very analogous to that for the free abelian group on two generators. That's right. That's right. That's right. So particularly since we're sort of running out of time here, I'm going to allow myself to be a little bit sloppy, do some things which I think make sense, but I'm going to start drawing a picture and then we'll try to interpret the picture and it's going to help us understand the universal abelian child's drawing, hopefully. Okay.
Okay.
So what am I trying to draw here? What's this picture that I want to try to draw here? It's something like, I'm going to draw a sort of picture of the universal abelian child's drawing. And I thought we've sort of indicated what that is in principle. But I'm going to draw a picture of it, but it's a weird mutant picture of it. We're going to have to interpret things in a funny way in order to understand what this picture is really doing. So what am I trying to say here? How does this work? It's like, what am I trying to say? It's something like green, blue, I'm trying to draw something very hexagonalish or equilateral triangular. So I'm stuck. You know, normally I like this square grid thing here, but it's probably more of a hindrance than a help at the moment. But I'll try to somehow fake it. So let's see. That's blue and that's red. And in some sense, what I'm drawing here is like the free quasi-abelian. I'm not quite sure what quasi-abelian means, but I'm drawing something very quandalish in a way. I'm drawing the free quasi-abelian reflective quandle, free quasi-abelian involutory quandle on 3 generators here. And it's like related to the mirror, right? The mirrors, I mean, there are Coxeter groups, but if you just take the mirrors of a Coxeter group, that it's the boundary mirrors, and you start reflecting mirrors across mirrors, you're like taking a quandle. You're conjugating one mirror by another, and it's all involutory. Everything's a reflection, so it's all, you know, it's called a reflective quandle. And in the non-abelian case, it would be very hyperbolic and something like that. But we're trying to abelianize here, so we're going to get something very abelian and relatively tame. I'm trying to draw what we get here. So let me see if I can draw what we get here. So it's something like this, something like this. It's color-coded in some funny way. Those are supposed to be our 3 generators. The vertexes are supposed to be our 3 generators, I think. Right. So there's some, right. This is a mutant picture. There's some sort of funny Poincare duality going on here, something like this. The vertexes in the picture I'm drawing now are supposed to be the mirrors in our universal abelian child's drawing. So we'll have to, so it's something like, yes, so we're going to reflect mirrors across mirrors, but the mirrors here are now just vertexes. So, right, reflection across a mirror is now, it's like a codimension 2 kind of reflection. You know what I mean? It's like, so it's in particular, it's not orientation reversing type of reflection. It's just, you know, the orientation preserving reflection across a point. So like if you reflect this green across this blue, you get a green up here. Something like there or something like that. And then you reflect the blue across that. Just keep on going, you get blue, you just keep on going.
Yeah.
Green, blue, and what color am I got here? This blue? Blue and then green, something. And, you know, on the green and the red, they're on this horizontal line. So I got like red, sorry, that's supposed to be red. Red, okay, red. So it's supposed to be a red there.
Yeah.
And I guess I could also put reds there.
Yep, so you get this.
Do you see the
lattice? Yeah, it's sort of a, well, mixed up, but yeah.
Well, I should draw a little bit more of it so you can see the general shape of it, because it's not just equilateral triangular, it's more like hexagonal or something like that. So what am I trying to say? There's like a blue there, and there's a blue. Am I doing this right? How does this work?
Yeah.
Blue there. And I guess there's like a blue thing there. And then there's let's see, this should be green right here. So it's like this. And
oh, wow.
There. What?
So you're never going to get the middle of this hexagon that you're...
Yeah, you never get this middle of this hexagon. And in fact, in the non-abelian case, what happens is those middles of the hexagons sort of act like punctures or something, and you unwrap infinitely around them. So it's like, there's some way to understand the non-abelian thing as a universal cover of this, in some sense, of this thing that we're going to try to draw here. But anyway, let's keep trying to draw a little bit of it here. So what am I trying to say? There should be a red line there. And so yes, well, another way to think of it is that it's actually just like an equilateral triangular. It's the usual equilateral triangular grid, but it's sort of doubled in size. So there are 4 different colors, and one of the colors is invisible. So that's a way to think of it. It's actually, right? If you just look at all the greens in here, they form a equilateral triangular grid, but sort of double the scale of the smaller grid. And then, you know, there's a red grid, and there's a blue grid, and there's an invisible grid. And those invisible dots are the ones in the middles of these hexagons. So we have enough of the picture to get a sense of how it looks. Let's see, what is this? This is green here. This is blue.
I'm gonna steal the screen for a second.
Sure.
Show you something, which is sort of the same
Okay.
thing.
So this is a picture you found online or something? Yeah, go ahead.
So is it like this thing here? So this is, in fact, I hadn't counted on the colors actually having anything to do with the colors that you were drawing, but this thing is called this kind of Kagame lattice.
That seems to be it. That seems to be it. Except that, you know, I went ahead and I drew the edges in colors too.
Yeah.
Which is not crucial, but it could be slightly helpful sometimes.
So it's called Kagame after some Japanese style of basket weaving where you put slats along these edges. And
okay, so I didn't know about this. I didn't know about this.
And it turns out that like...
All right, let me just write this down. Kagame, go ahead, yeah?
Yeah, so some kind of crystals can form this Kagame. They call it a lattice, although it's not mathematically a lattice. Form this Kagame lattice pattern, and they have lots of fun these days studying it. They like studying, I'm going to digress for one more minute.
Go ahead.
They like to study anti-ferromagnetic atoms, so that like each atom wants to be spin up or spin down and wants to point opposite from its nearest neighbors. But there's no way for them to all be happy here because of these triangles here.
Sorry, if I just, you know, Google Kagame, will it give me this anti-ferromagnetic stuff, or is there some?
Yeah, at least if you type Kagame lattice, you'll get that anti-ferromagnetic stuff.
Okay.
If you just type Kagame, you may get pictures of Japanese baskets, which would then show you why this is called Kagame lattice. Anyway, so it's interesting. I hadn't expected to see one that had pictures of red, green, and blue dots. That's even cuter, but
sure. But
anyway,
again, I'm just looking for buzzwords here so I can look this up later. Is this
another
statistical mechanics or
another good buzzword is frustration.
Frustration.
Because the famous example of a frustrated anti-ferromagnet. That's why
anti-ferromagnetic, you said? Maybe.
It has like tons of near ground states. It has no obvious energy minimizing state because of this frustration property. So it does a very interesting.
That's interesting.
Okay, I just thought I couldn't resist.
Sure, no, that's a good idea.
I don't know how related it is to what you're talking about, but it's.
Well, we're really trying to wrap up like really soon, but let's try to.
You have to reshare if you want me to see what you're doing.
Okay. Let me check.
I'm gonna have to quit soon,
what?
So yeah, I'm gonna have to quit soon, or I'll get.
Sure. We're trying to wrap it up in about 5 minutes. That sounds about right. 5 minutes.
Okay.
I mean, we could wrap it up right now, but maybe I can manage to find the little thing here. What am I looking for? I'm looking for the. Maybe it's over here. Exit full screen drawing. How do I do this? All right, okay, let's try the share screen. Screen to share.
Okay, yep.
It's working now?
Yep.
And I should just go like that?
Yep.
Okay. And so what am I trying to say here? Well, let's try to understand how to interpret this as a child's drawing, but first let's try to understand how to interpret it as a tiling. So you might almost think that this is a tiling, but it's a very funny kind of tiling. So what am I trying to say? What am I trying to say? It's this Poincare duality trick here. What am I trying to say? So it's hard to scroll back and forth between this thing and the original one. Let me just try to really quickly draw a picture of the original thing here. So we have. What are the colors? There's like a green there and a green there and a blue there and a blue there and a red there and a red there. And then it keeps on going, obviously. So first of all, this thing over here, the hyperbolic thing, this is non-abelian. This thing over that here we're drawing over here is abelian, right? I mean, you can see, right, this free abelian group on two generators, it ends up being sort of translations of this Kagome lattice. And so we're sort of trying to send up correspondence between the Kagome lattice and this Escher picture. But you have to remember that the correspondence is kind of non-reversible because the Escher picture is the universal non-abelian thing, whereas the Kagome picture is supposed to be a funny kind of picture of the universal abelian thing. So you have to give me a little bit of slack here. But the way the correspondence works is something like this, that the Escher picture has these cusps, these three colors of cusps, green, blue, and red. Now, what happens to the cusps in the Kagome picture? Do you want to take any guess about what's the geometric feature? You don't want to guess. It's the lines, the straight lines.
Okay.
And what do you think happens to the edges joining the cusps in the Escher picture? What do they become in the Kagome picture? And you should be able to figure this one out because
the dots, the points.
Yes, but you can say something better than that. I mean, right? You have the edges in the Escher picture join two cusps. So what does that correspond to in the Kagome picture? Because right, you've got.
I guess like a green dot would somehow be a reflection that's somehow related to is the process of switching to a neighboring red and blue.
Yes. But what I was fishing for that you were going to say that a green dot is the intersection of a red line and a blue line.
Okay.
So it's the intersection between straight lines. That's the Kagome analog of the edges joining cusps in the Escher picture. So, but on the other hand, the triangles in the Kagome picture, the small triangles in the Kagome picture are also the small triangles in the Escher picture. You know, and like, you know, a lozenge in the Kagome picture would be like one of these hourglass things.
Uh-huh. Well,
So, yeah, what?
Making a sort of dreamlike sort of sense, because I don't.
Yes, I mean, the picture doesn't look right. I mean, right, I'm taking the Kagame picture and I'm interpreting it as an abstract Coxeter complex. Or, is that the right word? Not a Coxeter complex, an abstract tiling. I'm interpreting the Kagame picture as an abstract tiling, but in this funny way, right? I mean, like we say, the edges in the tiling correspond to these intersection points in the Kagame picture. So you have to give this funny interpretation. But once you know how to do that abstract interpretation of the Kagame picture as a tiling, then you could go ahead and draw this actual tiling. But when I try to draw that tiling, it comes out it looks very busy in a way that I don't really understand. I would like to be able to actually see this universal appeal. I think part of the problem is that it really does have a high genus and things like that.
Huh.
So I think it's like, is it obvious? I think when you look at it from the right way, it's sort of obvious that it's going to be, it's going to be like an annulus with an infinite number of holes. And the holes are sort of arranged in a square grid. But it's very hard to get this picture it's very hard to see this picture. Whenever I try to actually draw this picture, it's a very, perhaps ugly picture, but at least very busy picture. It's like pleated like an accordion. I don't have a way to unfold it so that you can actually see it. But, but in principle, I'm just trying to wrap up for the punchline here, but I'm just trying to say, and there is no real punchline, but I'm just trying to wrap up here, that we're going to continue with this. We're going to try to continue to explore these abelian child's drawings, understand the universal abelian child drawing, and then understanding like the whole Galois correspondence for that universal abelian thing. And it will include all those rectangles that we were drawing, which will really just be the quotients of this Kagame lattice. So the finite quotients of this Kagame lattice, those will secretly be those rectangles that we were drawing in a previous discussion. And we're going to try to get this to work. We're going to try to understand it. We're going to try to do all sorts of things with it. Again, one of the things I really want to do with this is understand the genus of these abelian child's drawings. And of course, right, anytime you're studying the genus of, maybe particularly of, well, the genus of maybe of any surface, but particularly these abelian child's drawings, you really want to categorify the genus, so to speak. You want to think of the genus is just a decategorified version of the Jacobian variety. So we really want to understand the Jacobian abelian varieties of these abelian child's drawings. We want to understand them. We want to apply all our, ways that we like to learn about abelian varieties. We want to apply them to these Jacobians of these abelian child's drawings, which again, are just, so to speak, a categorification of the genus, in the sense that the genus is a decategorified version of the Jacobian. So all sorts of things I'm forgetting to say, all sorts of things I didn't get to because I'm running out of time. But I'm hoping we can continue with a lot of this. Boy, I didn't talk about lambda rings at all today. I really want to respond to the lambda ring ideas that you brought up last time. I have a whole bunch of stuff that I should be telling you. The whole lambda ring story that you told me about last time, I have a lot of response to that. And I was trying to write it down. I didn't succeed in writing it down this week. I was hoping I could talk about it today. Obviously, I didn't talk about it at all today. But that's another thing on the long list of things I really, really want to tell you about, either writing or talking here or something like that. But I'm sorry I'm running over so much. Anyway, thanks a lot.
Yep. Yeah, sorry, I got to go, but.
Okay. Sorry for being late. Sorry.
No problem.
Okay. Bye.
Sure. See ya.
Okay.